Good morning or evening.
Hello. So yeah, I think I will have a better internet connection also too. I had some issues with using two ways to connect to the internet, but one of them was kind of clunky last week, but now it's fixed.
Yeah, I had to restart my router again here. I just every day it's a new. It's like I don't know, roulette whether the internet will work. But so far it's fine during the lectures, so that's all that really matters.
All right.
Let's see.
Maybe
I'm gonna start the recording, and please start whenever you are ready. I'm just still dealing with the permissions on the YouTube, but you don't need to.
Yeah, sounds good. Yeah.
You don't need to wait for that.
All right. So hi everyone, welcome to the second week of the summer school and to the continuation of this course on the statistical mechanics of disordered systems. I think usually you do something, Luigi, for fixing the video, no?
What do you mean, sir? Oh, pinning you. Yes, I will do that. Thanks. Spotlight for everyone. Okay, you've been spotlighted.
So yeah, I'd like to start by summarizing what I think would be the most important takeaway from what we have done last week. So let me do that. This is a reminder of what we have done. So for me, the most important result was the identification of the limit free energy for these generalized versions of the Curie-Weiss model. So let me remind you how this looks like. So we had this free energy Fn of T and H. By definition, it was 1/n log of, so instead of sum, I write this integral against the general measure Pn. So I'm going to write integral of blah, 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 dPn of sigma. And then exponential of the energy function. And in the energy function, it's a generic nonlinear interaction term, this function xi or xi. And then some magnetic field H, sum of sigma I, dPn. Okay, so this was the quantity we wanted to study, and we have shown that as n goes to infinity, this converges to the supremum over m of T xi of m plus hm minus psi star of m, where psi star, so where psi is the limit of Fn of 0 h, so psi of h is the limit as n goes to infinity of Fn of 0 h, so which we assume exists. Okay, so this is part of the assumption, this limit exists. And moreover, we assume that this function psi is C1. Okay, and then psi star is the convex dual of the function psi. So one way to, we showed this using large deviations, and one way to remember the result is that the probability that this mean magnetization is around the value m is exponential of minus n psi star of m. Okay, this is what large deviations tell us. And so when n goes to infinity, we just optimize this function T xi of m plus hm, also taking into consideration that we pay a cost minus psi star of m to align magnetization to m. Okay, and I forgot to display the chat. Okay, so now I see the chat in case you say so. So are there questions on this? So for this specific model of Curie-Weiss, we could use large deviations to discover this limit for energy. But this is specific to this model, because the two other classes of models I want to discuss in this class, namely statistical inference and spin glasses, in these two cases, this large deviation approach will not be available, or at least I am not aware of any possibility to use an approach like this. And therefore, we need to think of another approach to recover this result, including in this for the simple case of the Curie-Weiss model. And it's nice to think about this specific model, which is simpler because we know in advance what the result should be. So we can just try to find alternative approaches to the same result. And that's going to be the focus of the next lectures. Okay, so how do we devise another approach to this result which does not rely on large deviations? And this will be based on this notion of viscosity solution. And before I go into this, let me say one more thing from last week, which is that once we have identified the limit for energy, we can recover meaningful information about the systems we care about. So in particular, I emphasized this mean magnetization under the Gibbs measure. This is obtained by computing the derivative in H of the free energy. And we have seen that at every point of differentiability, the derivative of the free energy converges to the derivative of the limit. And that was another thing I used last time, this envelope theorem. So if we differentiate in T, so let me clarify this also in relation with the question in the chat. So last time I mentioned this envelope theorem, which I did not prove. And this envelope theorem tells us, so I mentioned one version. Today I'm going to mention a slightly different version, which is slightly easier to justify. So the version I'm going to say today is, at any point where the limit is differentiable, if you want to compute the derivative, it suffices that you put the derivative inside the supremum, as if you kind of naively ignore it. You compute this quantity at an optimizer, okay? Whatever optimizer will do. Okay? The fact that it's differentiable tells you that any optimizer is fine. So in this case, you look at this function. If you differentiate in H, what remains is M. And so you know that at any point of differentiability of the limit, the derivative in H is M, where M is any optimizer of this formula. And so to answer the question in the chat, if you differentiate in T instead, then you see what happens is that instead it's this psi of M which will show up. So in fact, you're computing psi of M at any point of differentiability if you do that. And in terms of the Gibbs measure, what happens is that when we differentiate in H, it is this sum of sigma I quantity which comes down. So we are computing this angular bracket of sum of sigma I. So if you differentiate in T instead, it's really the same structure, but T is in front of this psi quantity. So then, in terms of, you will compute the angular bracket of this psi function of 1 over n sum of sigma I. Okay. Okay, so are there questions on this? And yeah, another thing I want to say is that this envelope theorem is part of problem set 3, and I wrote a solution to the relevant exercise in this problem set in the Overleaf project. So if you go to the course website or on my webpage, you will find an Overleaf project on which several of us are working. And so there are lots of files, and you go to SPS3, like solutions to problem set 3. And maybe you have to click on recompile if the document doesn't show up immediately, and you will see a solution to this problem set, to the correct exercise. So if you look at question 1b, this is the statement I just used today. Okay. All right, so after this short introduction, let me start with discussing viscosity solutions, or Hamilton-Jacobi equations. Yes, exactly. So there's a question in the chat about the fact that it sounds weird that we can put the derivative inside the supremum, but that's the statement of the envelope theorem. So I encourage you to look at the statement in problem set 3, exercise 1, and you will see that that is the statement, and you will see in the solution that we can prove it. So it's bizarre, it's counterintuitive, but it's true. And perhaps one way to understand it intuitively is that if you assume that everything is differentiable, then it would have to be such that the derivatives, if you take an optimizer, the derivatives of this quantity in M should vanish at the optimizer. And this gives you a relationship between the derivatives. And if you try to keep track of how, of what mistakes you do if you're not naive and you do not push the derivative inside the soup, then it's exactly this sort of, the derivative is vanishing term which justifies that the naive thing is actually correct. Okay, I don't know if I explained it well, but the statement is true. All right. So let's move on to this other topic, Hamilton-Jacobi equations, which I'm going to motivate indeed using the Curie-Weiss model. And I'm going to go back to the simple Curie-Weiss model. Okay, so I'm going to forget for a little while about this general, generalized version. Okay, so recall the definition. So for the standard Curie-Weiss model, the free energy looks like this. Okay, so I'm going to write 1/2 to the end because I find it perhaps somewhat more natural. So this is sum over I and j, and then sum over sigma I. Okay, so that's our free energy. And so recall also this bracket notation. So think of this as really being an expectation of f of sigma. Okay, so it's the expectation under the Gibbs measure. And by definition, this is the sum over sigma of f of sigma exponential of blah, blah, blah. Okay, I write dot, dot, dot. When I write dot, 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 it's always that you're copying this energy function, okay? Divided by the sum over sigma of exponential of blah, blah, blah. Okay, so the same T over N, sum of sigma I sigma j, plus H sum of sigma. Okay, so these are the definitions. And now, we restart from scratch. We want to understand how to compute the limit of this quantity. And we're not allowed to use large deviations. So how do we approach this? And okay, I already told many times that we're going to want to use partial differential equations. So let's see what happens if we take derivatives. We already know, and in fact, it's this question in the chat also. It's related to the question in the chat. We already know what happens when we take the derivative in H. Okay, so let's do this one more time. So let's review how this works. So we have this 1 over n in front. I'm going to keep it. Then the log, when I differentiate it, the result is that it's going to be the derivative divided by the quantity itself. And the derivative, it's this sum of sigma I here, which is going to pop out outside. So I can write sum, I can write sum over sigma of sum of sigma I, exponential of blah, 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 divided by sum over sigma of exponential of blah, blah, blah. And this indeed is the mean magnetization under this Gibbs measure. Okay, so so far so good. And as I alluded to before, if we differentiate in t, the same pattern will show up, right? When I differentiate in t, the only difference is that when I take the derivative, it's this 1 over n sum of sigma I, sigma j, which is going to come out in front of the expectation. So if I write it down, I get partial t fn. Okay, let me not write t and h. We understand there's t and h. This is going to be, okay, so if I pay attention, there's always this 1 over n here, and there's also 1 over n here. So in total, I will get 1 over n squared. Sum of sigma I, sigma j. Okay, and this, if I want, I can rewrite as 1 over n sum of sigma I squared, as we had already observed. Okay, so I guess now this clarifies fully the question that was in the chat at the beginning. So if we don't look very carefully, it seems that this t derivative is the square of the h derivative. So we are, it seems that maybe the difference between these two things is actually 0. But now that's not quite true because, when I look at dtfn, this is, the square is inside the bracket, while in this term, the square is outside the bracket. So let me write it. Oops. But still, it's an interesting observation that the right-hand side is actually the variance of something. This is the variance of 1 over n sum of sigma I. Right? That's interesting because 1 over n sum of sigma I itself, it's a quantity which is over the 1 or maybe less, but it's not a big quantity. Maybe at most it's over the 1. And now we're computing the variance of this quantity. So if we are a bit optimistic, we can hope for the fact that as n goes to infinity, maybe this variance becomes small because after all, we're taking a sum of a very large number of random variables, and we are normalizing the sum so that it's over the 1. So maybe the variance becomes small. If the sigma i's were IID, that would be true. So of course, in this context, it's under this Gibbs measure, they are not IID, but at least it gives us some hope. If we are of optimistic nature, we think that maybe as n goes to infinity, the right-hand side may become small. And so the question now is, can we actually make sense of this? Can we justify that indeed this variance will become small when n goes to infinity? And so here, one can think that it would be nice if we could relate this variance also to something that we can write in terms of Fn. Okay, because then we will have some closed equation that only involves Fn, and then we could just think about this specific equation. So you can ask yourself, can I express this variance in terms of Fn? And so Fn, so I guess some people would call it a cumulant generating function. I call it the Laplace transform. Some would call it log Laplace transform. In any case, the moments of the variables that are put inside this exponential, they are somehow encoded in the function Fn. So there should be a way to recover the second moment of sum of sigma I, for instance. And I'm not going to keep the suspense too long. This will be related to the second derivative of Fn. So let's try to compute the second derivative of Fn and see what happens. So it's nice in this case, if we want to compute the second derivative, it's nice to look again at this explicit expression here, because if I look at this one here, it's somewhat misleading because the bracket itself depends on h. So I have to differentiate the bracket in some sense. So I'm going to look at this expression in order to understand the derivative in h. And okay, I wrote dot, 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 so we don't see where h is, but in fact the h, it's here. And so it's appearing somewhere in the dots here and somewhere in the dots here. Okay. So when I differentiate, so I want to differentiate this quantity one more time. So if I differentiate the h, which is in the numerator, then another sum of sigma I will pop out. Okay, and so I'll get sum of sigma I squared divided by the same sum. So this will be the angular bracket of 1 over n sum of sigma I squared. And the square, 1 over n is outside, and then sum of sigma I squared. Okay, so let me write this first time, then I'll come back and deal with the denominator part. So partial h2 of fn is 2 terms, and the first one is 1 over n bracket of sum of sigma I squared. All right, now let's look at the second term. So for the second term, I want to differentiate the h which is hidden in this dot, dot, dot. So what will happen if I do that? Well, the sum in the numerator, you can just keep it aside. It's going to stay like this. And then when I differentiate this, okay, so it's going to be derivative divided by the function squared. So I will get another sum of another term which looks like this, divided by that denominator squared. Okay, so I'm not going to write it fully, but you can check that this is the angular bracket of sum of sigma I, and then squared, but the square outside of the bracket. Does that make sort of sense? Let me write it down, and so minus 1 over n sum of sigma I squared. So just so that maybe I can say again how this shows up. So we have this term which is going to stay fixed when we do this calculation. And ultimately, we will have this denominator squared. So instead of from the square, you decompose into 2 parts. You take one and you form one of these brackets sum of sigma I. And then the second one is really coming from when you differentiate the h and you have this u prime over u. Okay, we already used the 1u. Make sense? So this is the result of the calculation. And so indeed, this is related to the second moment of the variable. And in fact, it's particularly nice for us because in fact, it's exactly the variance, except for this little fact that the 1 over n is outside of the squares here, right? So this is actually n times the variance that we were looking for before. Right? So let's just combine these 2 displays. So conclusion. This expression, this difference between the first derivatives of fn, which we were hoping for, which we were hoping would be small, we have discovered it is 1 over n times the second derivative of fn. Let me try to single this out. Okay, so that again gives us some hope that as n goes to infinity, the right-hand side will become small. Because maybe at least in some places, this second derivative of fn will not blow up. And so we have 1 over n in front. And so hopefully things will be nice. Okay, so it gives us motivation to try to say that in the limit, you just write the solution in the limit will solve partial TF minus partial HF squared equals 0. It's not obviously following from what I showed, right? But it's just a plausible guess, let's say. And perhaps another thing we can verify is that because we are informed by this large deviation thing, we know what is supposed to be the limit. So we can also try and check if the limit does satisfy this equation. So let's do that. So the limit is f of t and h given by the supremum over m of tm square. So normally it's psi of m, but here psi is the square function plus hm minus psi star of m. And I told you this recipe from the envelope theorem that at any point of differentiability of f, if m naught is some optimizer of the formula for this choice of at this point of differentiability, then the derivative in t is m squared and m naught squared, and the derivative in h is m. So let me write this. At any point of differentiability of f, if m is an optimizer, m naught, let's say, then partial t f is equal to m squared, m naught squared, and partial hf is equal to m naught. Yeah, I should write m naught of t and h. Yeah, I'm doing this calculation at a given point. And so in particular, at these points, we do have that the relationship between the derivatives is valid. Oops. So this is true at any point of differentiability of f. Okay, so that gives us really a good motivation for a new approach to identifying the free energy, which is we start from this expression which is in the square, and we try to justify that in the limit, the right-hand side can be replaced by 0, and to say that therefore this identifies the limit. Okay, and we have to discuss also the initial condition. Let's observe a little bit what the initial condition is doing. So now you see why I chose t as the notation, because I'm going to think of t as some sort of time for our equation. It's like oftentimes I will call I may call t time, the time variable. Let me think for a second what I would say. Oh yeah, so let me talk about the initial condition. And this is something we have already observed several times. So when I said t equals 0, our free energy is just this Laplace transform of a sum of independent, identically distributed random variables. So you can factorize everything by independence, and you just get log of hyperbolic cosine of h. Okay, so this we can call psi of h. So what I argued here is that the limit free energy satisfies the following two properties. So first of all, this relationship between the derivatives. So at every point of differentiability, which is almost everywhere. So it's not difficult to show that if you have a convex function, then it's differentiable almost everywhere. Okay, so in fact, yeah, Lipschitz would suffice, but okay. If you use that it's convex, it's easier to show. And moreover, at t equals 0, we know what the function is. It's this psi function. Okay, is everybody with me here? So I'm observing that the limit is satisfying this property. No questions? You're all good? Thanks. So the question now is, yeah, so indeed this fn of 0h here does not depend on n. Like this function does not depend on n. It's because we have this product structure. When we say t equals 0, this thing does not depend on n. But when t is not 0, it does depend on n then, because we have these interactions. Oh, I use convexity to say that almost everywhere is a. So I argue that the equation is satisfied at every point of differentiability. And here I said I used almost everywhere instead. So I'm saying if your function is convex, then it's going to be differentiable almost everywhere. So it's kind of a cheap trick, but you know, if you just use that the function is Lipschitz, that's enough. And so the question that the first question that shows up is, are these relations characterizing the limit? Yeah, I have not justified yet that this is true. I'm just observing that we know in advance what the limit should be, and I'm observing that the limit satisfies this property. And the first question I want to ask before we try to understand this convergence question is this a characteristic property of the limit? Because if I struggle to justify this convergence and I say, okay, the limit must satisfy these properties, but then this is not characteristic of the limit, then this is not good enough. Okay, you know, I have failed to satisfy my goal, which is to identify uniquely the limit. If this is true, then essentially we could, you know, close basically all of the problems that I would like to talk about in the series of lectures, because things will be very easy. But as you have guessed, this is then not true. Like it is not true that if you say that the function, this identity between derivatives is satisfied almost everywhere, and the initial condition is fixed, this does not single out a unique function that satisfies these things. And that is the big problem that is going to occupy us. So unfortunately, the answer is no. So I claim that there are many functions which satisfy these two properties. So let me demonstrate this. I'm going to use a different initial condition, but I think it will not be difficult to adapt it to other initial conditions. So I'm also trying to pass the questions as I speak. So I'm pausing a little bit. So I'm saying that there is no unique solution in the sense that is written on the slides. Okay, I did not call it a strong solution or weak solution. I'm just saying that there is no uniqueness for this notion of solution. So let me demonstrate this. So before, yeah, let's play together with generating solutions to this problem without bothering too much about the initial condition. So if I just want to find solutions to this equation, I can look for affine functions. Now I can adjust the slope for t and h so that the relationship is going to be satisfied. So for instance, well, okay, the zero function is solution. Okay, without wondering about the initial condition. Of course, when I said not uniqueness, is for a given initial condition. But for now, I'm just exploring solutions without thinking about the initial condition. So if I look at the function t plus h, this is also going to be a solution because the t and the h derivatives are both equal to 1, so the relationship will be valid. And if I look at the mapping which gives t minus h, this is also going to be a solution because the derivative in h will be -1, but then I square it, and so I get 1 minus 1 equals 0. Okay, so I have these three solutions, and I want to use these as building blocks to negate uniqueness for a given initial condition. And to make my life easy, I'm going to use 0 as my reference solution. So I want to construct another solution which starts at 0. Okay, so this is one solution that starts at 0. I want to find another one which starts at 0. I'm going to do it like this. So these are the axes, and the blue part is the shape of the solution. This is a drawing for a fixed t. I'm plotting the function as a function of h, and the height is just the value of the function. And the point here is minus t. The point at the top is t, and here it's t. Okay, so you have this this corner which starts at the origin and then grows like this. And you see the way I built this function is this piece here is actually this t plus h function. And this piece here is the t minus h function. Okay, so we have already discussed that these are solutions. So it's clear that at any point which is not a corner, this will be a solution to the equation. Okay, because the piece here is the 0 function, which is also a solution. So you see, I've built a solution which is a piecewise made of solutions to the equation. So it's almost everywhere solving the equation. And well, clearly it is not the 0 solution. So I found two solutions which both start at 0, but which are different. And in fact, the non-uniqueness is rather dramatic because I can start this to grow this corner at any time I want. Instead of starting it at time 0, I can just wait for a little while at this 0 solution, and then at time 11.5, I start to grow my corner, and this will also be a solution. And I can also grow this corner wherever I want, not necessarily at the origin. So in fact, we have an uncountable number of solutions to a given equation with a given initial condition. So just to repeat the definition of the function. So if you give me a t, I'm going to describe the function ft, comma, dot. And I plot this function. So f of t, h is 0 if h is below minus t. Then it's t plus h if h is between minus t and 0. And then it's t minus h if h is between 0 and t, and then it's 0. Thanks. Yes, so now we have to come back to our first attempt at identifying a good notion of solution for this equation. So almost everywhere, solving the equation is not strong enough. It allows for too many solutions. So we have to strengthen this thing. So maybe we should say, okay, not almost everywhere is not good. We're going to say we're going to require this everywhere. So we could say, I want my function to be everywhere differentiable, and everywhere the relationships between the derivatives are valid. Now, there's another problem with this, is that we have seen already when we studied the Curie-Weiss model that this function f will have corners. You know, initially it's a nice parabola, but as t grows, at some point it starts to grow a corner at the origin, which, you know, when you compute the mean magnetization, it's responsible for this jump that Curie observed experimentally. So it's a problem because we cannot talk about these derivatives everywhere, because the function is actually not differentiable everywhere. You know, if we were to require the function to be differentiable everywhere, then there would be no solution to the problem. So we have to find some something intermediate between these two things. You know, asking everywhere is too strong. Asking almost everywhere is not strong enough. So how do we go about? And this is what viscosity solutions are meant to do for us. So let me try to give a So okay, let me just turn to this directly. So maybe it's a good time for a little break actually. So I'm going to start to discuss a notion of solution for these equations called viscosity solutions, and I'll take a 10-minute break for now. And of course, I'm happy to take questions. Maybe there were already some questions while I was doing. You know, you're saying, here is a function, and then we are computing some stuff, and we're observing the equation is satisfied. And then I'm just displaying the equation to you, and I'm asking, is your function the unique guy which satisfies the equation? There's no reason why the answer should be yes, right? I'm just, I take a function, I derive some properties of the function, and then I'm asking, oh, are these properties characterizing the function? Maybe yes, maybe not. I'm not sure. Maybe I misunderstood the question. Yeah. So there's an interesting question about the interpretation of this t variable, which I would like to call time because it's natural from the point of view of the equation. Yeah, the way I think about it is that we are scanning the. It's like back in the good old days when internet was slow and you were downloading an image, and initially it arrived, and maybe only the old guys remember that. So initially the image arrives and it's very blurry, and progressively you have more data coming up, and it's becoming sharper and sharper. Like to some extent, we are doing a little bit of something like this when we are sliding this function t, this variable t in this exponential. You know, when I think of this as you're trying to explore the landscape, and you know, when t is extremely large, this sum will be concentrated on the maxima of the energy to be like very sharp. And when t is very small, on the other hand, it's kind of blurry. It's kind of summing over all the configurations almost uniformly. And in particular, when t is 0, it's absolutely doing this uniform sampling. You know, like the measure is IID, and there you understand perfectly. And so, you know, perhaps one way to understand this t is that you're progressively sliding this this thing from this easy region where you understand everything to this like a sharper region where you don't quite understand the function. Okay, I'm not sure if this is such a good story, but that's how I think of it. I think, but it's not exactly the same as what physicists call renormalization, but to me, it carries some of the spirit of it. You're trying to relate what happens when you insist a little bit more on focusing on the extrema to the level just below. Yeah, okay. It's my 2 cents on this. Let's put it that way. Okay, so maybe I'll grab some water and then we resume. All right, so let me resume. Wait, maybe that's not exactly 10 minutes. I haven't paid close attention. So I would like to discuss a relatively generic form of these equations, not necessarily only in dimension 1 in this non-time variable, and also not necessarily talking only about the square function, because I want to display that just things work nicely irrespectively of these 2 considerations. So I'm going to give myself some function h, which is going to replace the square function. So yeah, there are many h's in my in this class. I'm sorry about this, but it's very customary for if you open any paper on Hamilton-Jacobi equations, on these equations we are going to discuss, this is denoted as h. So I feel I have to stick to that. I'm going to assume it's a locally Lipschitz function. Or if you want to see one function, it's not very important. So yeah, the goal here is to identify a well-posedness theory. Okay, that sounds like a fancy name, but well-posedness. I should have written for the equation. Okay, so I want to discuss this equation. So this, I'm going to call it Hj. So it's a Hamilton-Jacobi equation. So Hamilton-Jacobi. And so f is a function of, maybe I'm going to write like this. It's a function of t and x. So t is a non-negative parameter, and x is a variable in Rd. Okay, and when I write the gradient, I mean only the vector of derivatives in the x variable. So it's a d-dimensional vector. And the idea of viscosity solutions is that we want to so we may try to define the solution to Hj by doing the following thing. In fact, just as we have seen in Curie-Weiss, by just declaring that let's say by looking at the limit, epsilon going to 0 of the solution to the same equation, but with the second order term. I should write epsilon. Okay, so the thing is, if you add the second order term, even if epsilon is very small, this will regularize the problem, and then you can make sense of this equation without any problem. And then you can ask yourself, can you make sense of the limit when epsilon goes to 0? And for us, coming from this Curie-Weiss model, it's very natural because in fact we have seen that this function Fn, this free energy, is actually exactly solving an equation like this. So indeed, what we want to talk about is the limit of something of this form. And the point of these second order equations is that they satisfy a maximum principle. So if for each fixed epsilon, if you start from two initial if you look at solutions with two different initial conditions, and one initial condition is below the other, then the solutions will remain in this order for all future times. Okay, and we would like to express that even after we pass to the limit epsilon goes to 0, something remains of this maximum principle. Okay, so in some sense, I want to say that I only care about this class of solutions which are consistent with the maximum principle, even if the Laplacian has disappeared, which for each fixed epsilon is responsible for the validity of the maximum principle. So, okay, so maybe this was not super clear, but perhaps a more vague goal is that a bit like when we define weak solutions by passing derivatives to the test function, delta is the Laplacian, is the sum of the second derivatives. So if you want, for Curie-Weiss, we had this partial h twice. Okay, so if it was in dimension 1, this would be partial. Okay, so now I write x for the variable, but this would be this. Okay, but in general, it's the sum over all coordinates. So I'm going to play around and see if something remains of this maximum principle even after we pass to the limit. Yes, yes. So there's a question in the chat which I completely agree with, but you seem to suggest this is inconsistent with what I said, maybe. So indeed, the Laplacian is just the sum of the second derivatives in the x variable. So if it's if x is one-dimensional, it's just a partial h squared. I mean the second derivative in x. So in order to display this, let's say, reminiscence of the maximum principle, I'm going to do the following construction. So let's. And don't worry if you don't know what the maximum principle is. I'm going to take a smooth function, and I'm going to try to compute derivatives of that smooth function instead of computing derivatives of the limit. So it's a C infinity function. And let's say that we have a point such that f minus phi. So f is the function that is that I'm considering, and I'm trying to define what it means for f to be a solution. Or maybe I'm postulating that. Yeah, sorry, I take back what I said. Let's postulate that f epsilon converges to some f, and let's try to figure out properties of this f. So let me add here. Suppose f epsilon converges to some f. And I'm going to figure out some properties of f which are inherited from coming from this sequence of solutions. I take a smooth function and some point, and I postulate that f minus phi has a local maximum at tx. So I'm going to postulate it's a strict local maximum for convenience. So I like to make a drawing when I do this, and my drawing looks like this. So this, I think of this as being f. I put a corner so that I remember it's not the smooth function. And then I draw something smooth on top, and this I think is the smooth function. So this is f, this is phi, and you see that in this circumstance that I drew, at this point, we have a local maximum of f minus phi. Okay, so I have this point tx here. So you should think of this as being a d+1 dimensional drawing. But, okay, this is not super. Okay, so this is tx. So okay, so we have this. So if I go back to the before passing to epsilon goes to 0 limit, it should be that it's also true that f epsilon minus phi has a local maximum in the neighborhood of tx. Because since f epsilon converges to f, let's say the convergence is uniform. So it should be that, let me write, there should exist some t epsilon x epsilon converging to tx as epsilon goes to 0, and such that for each epsilon sufficiently small, f epsilon minus phi has a local maximum at tx. Okay, I'm going to admit this, but I think it sounds plausible at least. If you try to draw a function in my drawing here that approaches f, then in this uniform norm, then it will have a local maximum near tx. So now the advantage of the f epsilon. Oh yes, thanks for the question. I meant t epsilon x epsilon here. Thank you. And now f epsilon is smooth. So at this point, t epsilon x epsilon, we will have that the derivatives vanish because it's a local maximum. So same with the gradient. And now another important part is that we know something about the second derivatives as well, because the second derivatives cannot be, so it's a local maximum So it has to be that locally the second derivative points downwards, right? So it has to be that the second derivatives as a matrix, they are a negative matrix. So in particular, the Laplacian will be negative. Because if it was strictly positive, I could contradict the assumption that we have a local maximum. Yes, yes. The convergence I assume to be locally uniform. That's right. Okay, so I'm going to continue doing all the calculations at T epsilon x epsilon, but I'm going to write it explicitly one more time. So I told you I want to pass the derivative to the test function. So I'm going to try to compute partial T phi minus h of grad phi. And I'm going to do it at this special point, T epsilon x epsilon. So by the relationships above between the derivatives, this is the same as if I compute it for f epsilon, sorry. And now f epsilon solves the equation. Now f epsilon is a smooth function because we have added this Laplacian. So this is epsilon Laplacian of f epsilon at T epsilon x epsilon. Okay, but now I want to use this last property here. And you see that this Laplacian, it's crucial that it's showing up in this way, not minus Laplacian, for instance. So I want to replace this. So I want to say that this is smaller than epsilon Laplacian phi of T epsilon x epsilon. Now, what happens when I let epsilon go to 0 in this expression? Well, this phi is smooth. So if I let this go to, if I let T epsilon x epsilon go to Tx, this will just nicely converge. And phi is smooth here, so this will stay bounded, and there is epsilon in front. So the right-hand side will go to 0. Okay, and you see, it's crucial that I make this move because I don't know anything about this epsilon times Laplacian f epsilon. Maybe this does blow up. But if it blows up, it only blows up in one direction, towards the minus, towards the minus infinity. Towards the negative, I should say. Okay. And this really uses something extra about the way we constructed the solution, right? Because if I had built the solution, or if I had tried to build a solution with the minus Laplacian, I would not have been able to do this derivation. Okay, so it says something special about our way to construct a solution, something that remembers that there was a plus epsilon Laplacian before we pass to the limit. Okay, and this is what, at least this is how I think about viscosity solutions. It's this thing that remember that there used to be a tiny amount of Laplacian with the correct sign somewhere. Okay. So okay, the definition of viscosity solution will be based on this observation. That's why I'm making this comment. And I could also do it the other way around. If I touch my function f from below, then I will have the converse inequality as the one I derived here. Okay, so let me summarize this into the definition now. Okay, so let's say for a given continuous function f, so I give myself a continuous function f, and I want to say when it is that it is a solution to the equation. And I'm going to do it in two halves, because one half is only dealing with touching the function from above, as we discussed more carefully, and the other part is touching the function from below, and then being a solution combines the two aspects. So let me write this. So we say that f is a viscosity subsolution Oh yeah, and I should say viscosity comes from the way I discussed, this epsilon times Laplacian. You can call this the viscosity, a small viscosity. Epsilon, you can call it the viscosity parameter. Well, not important. So F is the viscosity solution to our equation. Remember, I called it Hj. Whenever we can touch it from above, the inequality displayed on the slide is valid. So for every Tx in 0 infinity cross Rd and phi smooth. Okay, so phi is also a function of T and X. If f minus phi has a local maximum at Tx, then the inequality above is valid. So let me rewrite it. Then dt phi minus h of grad phi at this contact point is non-positive. Okay, so again, my drawing is, I touch f from above, and this allows me to say that f cannot be going too large, and so this corresponds to this partial t thing being a non-positive. Okay, I want to make sure that my function does not go too high, but maybe it goes down quite a bit if I only touch it from above. Now I'm going to do the other half, the viscosity super solution. So that's the first part. Second part, we say that F is a viscosity super solution to the equation. If so, very similar, it's just the other way around. For every Tx in 0 infinity course Rd and the smooth function phi, if f minus phi, so this time we touch from below, so f minus phi, we have a local minimum at Tx, then the converse inequality is valid. Okay, and in this case, my drawing will be that f is like this and phi is like this. So this is f, this is phi. Okay, and I'm thinking that I'm touching here. Okay, and now if a function f is both a sub-solution and a super solution, we're going to say it's a solution. So I'm going to often suppress viscosity. Okay, I'm going to just say sub-solution instead of viscosity solution. Yeah, I'm going to comment on this question. That's a good question. Okay, so yeah, a few comments. So indeed, the question in the chat is quite relevant because when I did the derivation, I assumed strict local maximum in order to argue by approximation. So you can check that the definition is in fact equivalent whether you write local maximum or strict local maximum. And the reason is that if you manage to create one direction is obvious. If you have a strict local max, then you have a local max. And if you give for the converse, if you give me a function which, so if you're in this situation where f minus phi has a local maximum at tx, but you're not sure if it's strict, and you could bend a little bit. Sorry, phi is like this, so you could bend a little bit phi by adding a parabola centered at tx, and this will make it become a strict local maximum. And if you just add a parabola, the derivatives of the function at tx will not change. So in fact, you can work your way around this. Yeah, that's a good question. So I should maybe I'm not going to write it explicitly, but it's important to notice that this definition does not depend on whether or not you write strict in the strict local maximum expression. And in fact, it's one of the exercises in the fourth problem set is exactly this. And another question you can ask is also, can you weaken the phi being smooth, infinitely differentiable assumption? And another question in this problem set is to show that it's equivalent if you just require phi to be C2 instead of C infinity. Yes, so indeed, there's another question about if we were considering the equation with the minus Laplacian instead, so we would end up with the inequalities going the other way around here and here. And there we would have difficulties indeed. So it would not, like, for now I just stated definition, so nothing bad has happened so far. But it's a bad idea to try to solve the backwards fit equation, and it shows in this context, because for instance, we will want to prove uniqueness of solutions to this equation, and the proof would break down if we were doing this interchange. So it's a very interesting question because it seems that we're dealing with any sort of nonlinearity, but it's not quite true. Okay, so maybe I should not say it breaks down, but it's just that you would have to phrase it like the only way you can make sense of the, when I want to talk about uniqueness, I would want to say that if I fix an initial condition, then I have unique solutions. But if I put the Laplacian backwards, then when I observe what's going on with my with my comparison principle, I will have rather that if two things coincide at the final time, then they coincide before that, which is not going in the good direction. Anyway, like it's like yeah. So indeed, it's quite an interesting observation because yeah, okay, so that's another way to make the thing work for the local maximum, I guess. But yes, so it's interesting to keep in mind that there's something which is not completely innocent going on here. Like when I do the drawing, I I think of phi as being above the true function, and I think of myself as trying to make sure that the f is not going too large, and this is consistent with the time derivative being non-positive. I want to say over time this is going to go down. So there's some consistency between putting a smooth function on top of the function and asking the derivative to be in time to be negative. Anyway, this is a central point, and it's a very good question. Yeah, one last comment, which is less important, that I would like to do is that this point Tx, where the local max or the local mean is achieved, I like to call it a contact point. And I like to think that these functions, they actually touch here. In fact, at the contact point, phi and f are actually equal. And this is really without loss of generality, because the equation we are dealing with only looks at derivatives. So if I want, I can always shift all of my functions by constants. Okay. So from now on, I will often call this Tx the contact point. And I will also often think of these things as touching functions. And touching from above, touching from below are expressions I'm going to use. Oh yeah, perhaps one last thing, of one last vocabulary comment. We may say that F is a viscosity solution to when I say it's a viscosity solution to some inequality, like this one displayed here, I mean that it's a viscosity subsolution of the equation with an equal sign instead. If F is a subsolution to the equation, it's just a notation convention. Are there questions on this definition? So it's nice to also notice that if the function is C2 at a given point, then you can touch it by a smooth function from above and from below, and making sure that the derivatives coincide. I mean, when two functions touch anyway, the derivatives will coincide. So if you have a point where the function is C2, then you can touch it from above, and you can use that. Let's say it's a solution. You can use that you can touch it from above and from below, and from that you see that the solution will solve the equation at this point. Okay, so if you have a function which is globally C2, then it will solve the equation everywhere. Okay, so at least this notion of viscosity solution is not completely crazy, because if my function is actually sufficiently smooth, then it's going to solve the equation everywhere. Okay, but hopefully it also deals nicely with situations where the function is not smooth everywhere. Okay, so perhaps one more thing we can do is verify that. I gave you a counterexample to uniqueness at the beginning with this function which has a corner like this. And so I would like to check that this notion of viscosity solution just introduced allows me to rule out all of these spurious solutions. And I would like to say that the zero solution is the true solution, because for some reason I find it more natural. And I would like to say that the solutions which start to grow corners at random times, and these are places, these are ruled out. Okay, so let's see. Let's go back to So you remember the function was like this, with the h here, and this was for fixed time. This is as a function of h minus t, t, t. So I would like that this is not a viscosity solution. To the equation we were thinking about at the time. So here, this one was for initial condition being 0. Yeah, I would like to say that this is not a solution to this equation. So I need to find a way to touch this function from above or from below. And surely the problem will come from one of these corners. Okay, so if I touch this function at a point where it's smooth, then nothing particular will happen. So I have to play with the corners, and I'm going to try with the one at the middle. So I'm going to try to touch it here. So let's say I'm going to take as my smooth function, I'm going to take phi of t and h, which is just t. So that's f minus phi. This is always non-positive, and f minus phi of t0 is always 0. Okay, so in fact, this gives me lots of contact points because any t comma 0 is a local, so it's a local maximum of f minus phi. So if f was a viscosity solution, I should have that the equation is satisfied for phi at any of these points. So f is the test function, okay? This is f. But this is false, because the left side is equal to 1. Okay, the time derivative is 1. Okay, and this is good news for us. Okay, we want to say that this is a bad function. We won't say it is not a viscosity solution. And indeed, this is a proof that it is not a viscosity solution. All right, so I think with all we have now, we're in good shape to prove the following result. I'm going to postpone the proof to next time, but I want to state it. So proposition. So, okay, let me say, I want to go back to the Curie-Weiss model with this function fn, and I want to say any possible limit of fn is going to be a viscosity solution of the equation. Okay, so yeah, let me do it more slowly. So maybe I'm hesitating if. So back to Curie-Weiss. So here I'm, for a while we discussed this notion of viscosity solution, and now I want to reassure myself that indeed this free energy of the Curie-Weiss model, we can say that if it converges to something, then this limit must be a viscosity solution. Because if I cannot do that, this is also not a good notion for me. Because I want to manage to do two things. First, to say that my limit of Fn is satisfying certain properties, and second, that these properties characterize the limit uniquely. And so I have to worry about the two aspects, but it's kind of easier for me to settle down first the aspect of Fn converges to a viscosity solution. Because with all we've done today, basically we have already done the argument. I just have to repeat it. So I'm going to state it. So Fn, the free energy of the standard Curie device. And here is a proposition which you can think about before next time. So let F be a subsequential limit, any subsequential limit, in the sense of local uniform convergence. Then F is a viscosity solution to this equation. Okay, so I think it's really a good exercise if you want to do it, to think about how to prove this, because it's really reusing the things we discussed today. So if you manage to prove it, it means you have understood well what I tried to describe. Other questions? So then I'll make some more comments. Yes, I want to. Oh, you're absolutely right. Thanks for this comment. This should be like this indeed. Yeah, thanks a lot for this comment. So please pay attention to the fact that I had made a serious typo here. Subsequential, I mean, let's assume that F converges along a subsequence. Sorry, so that Fn converges along a subsequence to a function F in the sense of local uniform convergence. Maybe I should have said, assume that there exists a subsequence phi n such that F phi n converges locally uniformly to F, then that result is true. Yeah, so I want to make just a handful of comments about the problem sets, because there are many problems and I want to make sure you manage to orient yourself in the jungle of problems. So the second problem set was for this easing model on the grid, and it's really a bit off topic. I think it's very interesting, but it's somewhat separate from the core of what I want to discuss. So if you have not thought about this very much, no problem. The third problem set, there are two exercises, and the first exercise was really about exploring this envelope theorem. And I wrote a solution to this problem set, as I mentioned earlier. And I encourage you to look into at least the statement, and maybe at least also a little bit into how the proof works, especially the second version, like 1b in the problem set. This is relatively easy to prove. And so, it doesn't take too much time to read the proof and be like, okay, this I understand. So it justifies that if this function supremum is differentiable, then you can do this operation of putting the derivative inside the soup. Okay, and then the second part of this problem set is about trying to understand the magnetization of the Curie-Weiss model using the results we have obtained. So it's interesting, and but perhaps it's interesting that you realize that we can understand these objects well if we spend enough time. It's a study of the limit object itself. Okay, so I told you that the core goal of the course is to understand how to identify the limit. And I kind of leave aside, like to problem sets or elsewhere, how we analyze the limit. But so in this second part of this third problem set, this is where we discuss how to analyze the limit. So it's nice if you have a look at it, but again, it's not like in the mainstream of the emphasis of the series of lectures. And so now I'm moving to the fourth problem set, and in the fourth problem set, we start to play around with the definition of viscosity solution. So I really encourage you to think about the first few exercises of this problem set. I mean, in particular, exercises 1, 2, and 3, because they relate very much with what we discussed today. I think they are relatively doable. And then, there are more problems because I want to make sure nobody gets bored, but if you manage to do problems 1, 2, and 3, that's really great. And yeah, tomorrow, this will also show up to some extent. Yeah, so thanks for your attention, first of all, and I'm happy to take more questions if you have.
Well, I have a question. So this is a little bit philosophical, and you address a version of it of the question in one of your papers. But when you move from this special case to the general, where you have this function psi,
yes,
in principle, you could absorb the h times sum of sigma I into the psi, but you don't.
That's true. It's because yeah. So especially in the approach with large deviations, it's bordering ridiculous to not do it. But then when we do the partial differential equation, it makes more sense. So maybe I have not let you finish your question. Sorry.
Well, no, I was just wondering if you had any. I mean, in one of your papers, you talk about how this term kind of naturally arises as an order parameter for the problem, but I'm wondering if in the sort of version of the story you're telling here, there's a natural way to see why not to absorb that term.
Yeah. So in fact, let's imagine for a second that initially we're only caring about understanding the free energy for the model without this extra guy. So let's say I start with Curie Weiss, and the only thing I want to understand is the limits of this object. And that's it. So I can give it a name. I can call it Fn of t. But it's not, yeah, it's like I want to do something a little bit like large deviations, where I leverage on understanding some simpler thing, like I'm not exactly sure how to describe it, but if I only focus on this quantity, I will be a bit stuck. So my first task, in some sense, is to find a way to enrich the energy so that the extra guys I add are simple enough. So I don't want interactions in these simple guys. And yet they help me to find a closed equation for the free energy. So it's a bit of a heuristic goal, not very well defined, but
Right.
when we do the extension with the H, at least in practical terms, it does two nice things for us. One is that we can find a relationship between the derivative of this quantity. That's one thing. And the other thing is that when I said t equals 0, I understand the function perfectly well. And that's always the sort of thing that we are trying to shoot for. And you can say, okay, why did you choose this term specifically? But already when I face this first quantity, if I differentiate in t, I see that what shows up is this. When I compute the partial differential, the partial derivative in t of the first equation, what I will get is this 1 over n sum of sigma I everything squared. And so if I believe that that this quantity does not fluctuate too much, then it gives me some hint that that if I could have some other parameter that when I differentiate, I get that same quantity but without the square, then I would get a relationship. So maybe by postulating concentration of the quantities that show up, you can guess. At least you can try some guess for what is the. But it's a little bit. I don't have a perfect answer to your question. It's a little bit of a dark art, I would say. Especially for spin glasses, if physicists had not built all of their intuition for how things behave, it would have been very hard for me to come up with the right enrichment. Probably I would not have managed it. Yeah, so indeed, for this notion of viscosity solution, you don't need to assume that H is only a function of grad f. So let's say, okay, so it depends. Yeah, it depends on what else you want it to depend. So you can do you can consider versions where it depends also on the second derivative, and basically everything works, but some of the proofs become more complicated. So I will use in the proof of the uniqueness argument that it's of first order, and it would be a bit more complicated, but still true if it was second order. You could also imagine it depends on t and x. Now it could be that that the h is like h of tx grad f of tx. And that also will not cause any problem in this. At some point very late in the lecture, I will use that it is not depending on t and x, but for most of what we're going to do, you can also consider this generalization. And this it's more harmless. Like for the uniqueness part, you can just fix the proof without difficulty if it depends on t and x. I mean, you have to assume some continuity in t and x also, but it's okay.